So here's something to think about as you settle in tonight. Right now, wherever you are, there's heat moving. It's radiating off your body into the air around you. It's conducting through the pillow beneath your head, through the walls of whatever room you're in. The warmth from your last cup of tea or coffee is slowly, quietly dissipating into the universe, spreading out, becoming less and less concentrated with every passing second. And that process, that gentle, invisible, unstoppable flow of heat from where there's more of it to where there's less, that's one of the deepest truths we've ever uncovered about how the universe works. It took us thousands of years to understand it, and honestly, we're still working on some of the implications. Thermodynamics. The word itself sounds heavy, academic, maybe a little intimidating, but strip it down and it's just two Greek roots smashed together. Thermi, meaning heat, and dynamis, meaning power. Heat power. The science of what heat does, where it goes, and what you can make it do for you. And the story of how we figured all of this out is one of the great intellectual adventures in human history. It involves fire, steam, war, genius, rivalry, tragic early deaths, and at least one fundamental law of nature that tells us the universe is slowly, irreversibly winding down. Which sounds dramatic, but we'll get there. For now, let's start at the very beginning, and I mean the very beginning, because humans have been thinking about heat for a long, long time. Think about fire. You've sat in front of a fire before, right? A campfire, a fireplace, even a candle. There's something almost hypnotic about it. And for most of human history, fire was the only real technology we had for manipulating heat. We could make it. We could contain it. We could use it to cook food, to harden clay, to smelt metals. But we didn't really understand what it was, not in any deep way. We knew that wood burned. We knew that some things burned and other things didn't. We knew that fire was hot and that heat could be useful. But the question of what heat actually is, what's really happening when something gets warm, that question turned out to be spectacularly difficult to answer. And for most of recorded history, the best answer anyone had was basically wrong. Let's go back to ancient Greece, because that's where a lot of Western thinking about the physical world gets its start. Aristotle, writing around 350 BCE, proposed that everything in the world was made of four fundamental elements: earth, water, air, and fire. Fire wasn't just a process or a reaction in his framework. It was a substance, a fundamental building block of reality, right alongside dirt and water. And that idea, that heat, was somehow a thing, a stuff, something you could add to an object or take away from it. That intuition stuck around for an astonishingly long time. More than 2,000 years, in fact. It feels natural, doesn't it? When you heat up a pot of water, it really does feel like you're pouring something into it. The water gets heavier with heat, fuller, more energetic. The language we still use reflects this. We talk about heat flowing, about adding heat, about heat capacity, as if objects are containers that can be filled up with warmth. That metaphor is so deeply embedded in how we think that even today, even knowing what we know now, it's hard to shake. But I'm getting ahead of myself. Let's stay in the ancient world for a moment, because there's another thread worth picking up. The Romans were extraordinary engineers. They built aqueducts, roads, concrete structures that are still standing 2,000 years later. And they were very good at using heat practically. Their bathhouses, the famous thermi, used sophisticated systems of underfloor heating called hypocausts. Imagine this. a raised floor supported by stacks of clay tiles, with a furnace at one end burning wood continuously. Hot air and smoke would flow through the space beneath the floor, heating the tiles, which would radiate warmth upward into the room above. The Romans even ran clay pipes through the walls to distribute heat more evenly. It was, in a real sense, the first central heating system, and it worked beautifully. But here's the thing. The Romans who designed these systems had no theory of heat transfer. They didn't know about conduction or convection or radiation as distinct mechanisms. They just knew, from experience, from trial and error, that hot air rises, that stone holds warmth, that if you put the furnace at the right end and sloped the floor just so, the heat would distribute itself through the building. Practical knowledge, hard-won and effective, but without any underlying framework to explain why it worked. And that gap between practical mastery and theoretical understanding is a recurring theme in the story of thermodynamics. For centuries, people who worked with heat every day, blacksmiths and glassblowers and brewers and cooks, they accumulated enormous practical wisdom. They knew exactly how hot a forge needed to be to work iron versus steel. They knew how to temper a blade, how to control a kiln, how to manage the heat of fermentation. But ask them what heat was, and they'd shrug. It was fire. It was warmth. It was just heat. The theoretical framework lagged centuries behind the practical knowledge, and when the theory finally did start to develop, it came from some surprising directions. Now, let's jump forward quite a bit, past the medieval period, past the Renaissance, to the 17th century, because that's when things really start to get interesting from a scientific perspective. And the person I want to tell you about is a man named Robert Boyle. You might recognize the name from chemistry class. Boyle's law, the one about the relationship between the pressure and volume of a gas. But Boyle was much more than that one law. He was born in 1627 in Ireland, the 14th child of the Earl of Cork, which made him fabulously wealthy and gave him the freedom to spend his entire life doing exactly what he wanted, which was experimenting. He was one of the founding members of the Royal Society in London, and he was obsessed with understanding the nature of matter and, crucially, the nature of heat. Boyle did something that seems obvious now, but was genuinely radical at the time. He insisted on actually measuring things. He built air pumps. He constructed thermometers. He ran careful, repeatable experiments. And one of the things he demonstrated, working with his brilliant assistant Robert Hooke, was that when you compress air, it gets hotter. Push a piston down into a cylinder of air, and the air warms up. Let it expand again, and it cools down. Think about that for a second. No fire involved, no flame, no burning, no obvious source of heat. Just squeezing air, and it gets warm. Where was the heat coming from? If heat was a substance, some kind of fluid that flowed into things, then compressing air shouldn't create heat. There was no source for the fluid to flow from. This was a crack in the old theory, a hint that something more fundamental was going on. But Boyle didn't quite put it all together. He was working at the edge of what the science of his time could handle, and the conceptual leap required to explain what he was seeing wouldn't come for another century and a half. Still, his insistence on careful measurement, on trusting experiments over philosophical speculation, that set the stage for everything that followed. He showed that heat behaved in ways that were lawful, predictable, measurable. It wasn't mystical. It wasn't divine fire or philosophical essence. It was something you could study, quantify, and eventually understand. Now, around the same time Boyle was working, there was another crucial development happening, and it's one of those things that seems so basic we take it completely for granted. The thermometer. You'd think measuring temperature would be straightforward, right? But it's actually a surprisingly tricky problem. The first real attempts at building thermometers came in the early 1600s. Galileo, yes, that Galileo, built a device called a thermoscope around 1593. It was basically an inverted glass tube with a bulb at the top, sitting in a dish of water. As the air in the bulb warmed up, it expanded and pushed the water level down. As it cooled, the water rose. Clever, but it had a major problem. It was also sensitive to changes in atmospheric pressure, so you couldn't tell if the water level was changing because of temperature or because of weather. It measured something, but it wasn't purely temperature. The sealed liquid thermometer, the kind you'd recognize, came a few decades later. Daniel Gabriel Fahrenheit, a German-Dutch instrument maker, perfected the mercury thermometer around 1714. And here's a detail I love about Fahrenheit. He was obsessed with precision. Absolutely obsessed. He figured out how to purify mercury so that it would expand uniformly with temperature, and he calibrated his instruments with extraordinary care. His temperature scale, which we still use in the United States, was originally based on 3 reference points: the coldest temperature he could reliably produce in his lab using a mixture of ice, water, and ammonium chloride, which he set at 0, the freezing point of pure water, which he set at 32, and human body temperature, which he set at 96. The numbers seem arbitrary, and honestly they kind of are, but the precision of his instruments was remarkable for the time. A few decades later, Anders Celsius, a Swedish astronomer, proposed a simpler scale: 0 for the freezing point of water, 100 for the boiling point. Though, amusingly, Celsius originally had it backwards. He put 0 at boiling and 100 at freezing. It was flipped after his death. But the point is, by the mid-1700s, scientists finally had reliable tools for measuring temperature. And that matters enormously, because you can't build a science of heat without being able to measure it consistently. You can't discover laws if you can't quantify what you're observing. And this brings us to one of the most important and most misunderstood concepts in the early history of thermodynamics: the difference between heat and temperature. Because they're not the same thing, and figuring out that they're not the same thing was a genuine breakthrough. The person who made this clear was a Scottish chemist named Joseph Black, working at the University of Glasgow in the 1750s and 1760s. Black noticed something that anyone who's ever watched ice melt has seen, but probably never thought deeply about. When you take a block of ice and put it in a warm room, it starts to melt. But here's the crucial observation. While the ice is melting, its temperature doesn't change. It stays right at the freezing point, 32 Fahrenheit, 0 Celsius, the whole time it's transitioning from solid to liquid. Heat is clearly flowing into the ice from the warm room, but the temperature isn't going up. So where is the heat going? Black called this latent heat, hidden heat. Heat that was absorbed by a substance without changing its temperature. Heat that was being used to change the state of the material, rather than to warm it up. And this was a profound insight. It meant that heat and temperature were fundamentally different quantities. Temperature was something you could measure with a thermometer. Heat was something else, a quantity of something that could flow into or out of a substance and either change its temperature or change its state, but not necessarily both at the same time. Black also discovered what he called specific heat, the fact that different substances required different amounts of heat to raise their temperature by the same amount. A pound of water takes a lot more heat to warm up by 1 degree than a pound of iron does. Think about that in everyday terms. It's why a metal spoon left in a hot pot feels burning hot, while the wooden handle stays cool. It's why coastal cities have milder climates than inland ones. Water absorbs and releases enormous amounts of heat without changing temperature very much. So the ocean acts as a massive thermal buffer, moderating temperatures along the coast. That's Joseph Black's discovery, playing out across the entire planet's climate system. Now, Black was doing all of this work in Glasgow in the 1760s, and here's where the story takes a turn that changes the entire world. Because working in the same university, literally in the same building, was a young instrument maker named James Watt, and Watt had been given a model of a Newcomen steam engine to repair, a clunky, inefficient machine that had been used to pump water out of mines for decades. And as Watt studied the engine, trying to figure out why it wasted so much fuel, he started talking to Joseph Black about heat, about latent heat, about how steam behaved when it condensed back into water. And those conversations, between the chemist who understood heat and the engineer who understood machines, those conversations were about to light a fuse under the entire Industrial Revolution. Because Watt didn't just tinker with the Newcomen engine. He thought about it. He obsessed over it. And what he realized, thanks to those late conversations with Black, was that the Newcomen engine had a fundamental thermodynamic problem, not just a mechanical one. Let me walk you through it, because it's worth understanding how the Newcomen engine actually worked. Picture a large vertical cylinder with a piston inside it. Steam from a boiler fills the cylinder, pushing the piston up. Then, and here's the key step, a jet of cold water sprays directly into the cylinder, condensing the steam back into liquid water. When steam condenses, it shrinks dramatically. A given volume of steam turns into a tiny fraction of that volume as liquid water, so the pressure inside the cylinder drops way below atmospheric pressure. The atmosphere, pressing down on the top of the piston, pushes it back down. That downward stroke does the useful work, pulling on a chain connected to a pump rod that lifts water out of a mine. Then more steam fills the cylinder, the piston rises again, cold water sprays in again, and the cycle repeats. It worked. It had been working since Thomas Newcomen built the first practical one around 1712. Mines across England used these engines, but they were astonishingly wasteful. They burned mountains of coal to do relatively modest amounts of work. And Watt, with Black's insights about latent heat fresh in his mind, could see exactly why. Here's the problem. Every time you spray cold water into that cylinder to condense the steam, you cool the cylinder walls down. The thick iron cylinder drops to nearly the temperature of the cold water. Then, on the very next stroke, you need to fill that cylinder with hot steam again. But the steam doesn't just fill the space. It immediately starts condensing on those cold cylinder walls, giving up its latent heat to warm the iron back up. A huge fraction of the steam you send in is wasted just reheating the cylinder. It never gets to push the piston. It just condenses on contact with cold metal, surrendering all that latent heat Black had so carefully measured. You're essentially throwing away energy every single cycle, heating and cooling the same chunk of iron over and over and over again. Watt saw this clearly. The cylinder needed to be hot to receive steam efficiently, but it also needed to be cold to condense the steam and create the vacuum. Those two requirements were in direct conflict, and the Newcomen engine tried to satisfy both of them in the same vessel. It was like trying to use one room as both a freezer and an oven, alternating every few seconds. Wildly inefficient. And the story goes, and Watt himself told this story years later, so we have it in his own words, that the solution came to him during a walk on Glasgow Green on a Sunday afternoon in 1765. What if you didn't condense the steam inside the cylinder at all? What if, instead, you connected the cylinder to a separate vessel, a separate condenser, that was kept cold all the time. At the right moment in the cycle, you'd open a valve, the steam would rush out of the hot cylinder into the cold condenser, condense there, create the vacuum there, and the cylinder itself could stay hot the whole time. You'd never waste energy reheating it. It sounds simple when you say it like that. Just put the condensation somewhere else. But think about what Watt was really doing. He was applying Black's concept of latent heat as an engineering principle. He understood that the enormous amount of energy required to convert water to steam and released when steam converted back to water was the central fact of the engine's operation, and that managing where and how that conversion happened was the key to efficiency. He wasn't just fixing a machine. He was reasoning from thermodynamic principles to redesign a system. That's a different kind of engineering. That's engineering informed by science. And in the 1760s, that was genuinely new. Now, it took Watt years to actually build a working engine with a separate condenser. Years of frustration, financial difficulty, failed experiments with materials that couldn't hold a seal, cylinders that couldn't be bored accurately enough. He nearly went bankrupt. He took on work as a surveyor and canal engineer just to keep food on the table. It wasn't until he partnered with Matthew Boulton, a Birmingham manufacturer with deep pockets and sharp business instincts, that the Watt engine finally became a commercial reality in the mid-1770s. Boulton and Watt engines were roughly 3 times as fuel efficient as Newcomen engines. 3 times. That's not a marginal improvement, that's a transformation. Suddenly, steam power was economical enough to use not just at coal mines, where fuel was essentially free, but at factories, mills, ironworks, anywhere. And that, more than any single political event or cultural shift, is what powered the Industrial Revolution. But here's what I find really beautiful about this story. It's a story about the gap between knowing something and understanding it well enough to use it. People had been boiling water and watching steam push lids off pots for centuries. Newcomen had built a working steam engine 60 years before Watt improved it. But it took Black's careful, patient, almost philosophical work on latent heat, work that seemed abstract, work that was about measuring how much heat ice absorbed as it melted, to give Watt the conceptual framework he needed to see what was wrong and imagine how to fix it. The science didn't come after the engineering, trying to explain it. The science came alongside the engineering and made it better. That feedback loop between understanding and building, between theory and practice. That's going to be one of the great themes of thermodynamics going forward. So Watt's engine is humming along, transforming industry, and the world is starting to ask bigger questions about what these engines are actually doing. Not just how to build them better, but what, fundamentally, is happening when heat produces motion. What are the rules? Are there limits? Can you keep making engines more and more efficient forever, or is there some boundary you can never cross? And this is where a young French military engineer enters the picture, and honestly, his story is one of the most poignant in all of science. His name was Sadi Carnot, and he was born in 1796, the son of Lazare Carnot, who had been one of the most powerful men in revolutionary France, a mathematician, military strategist, and member of the Directory that governed the country. Sadi grew up in a household steeped in both mathematics and political upheaval. His father had been exiled after Napoleon's fall, and the family's fortunes rose and fell with the tides of French politics. Sadi himself trained at the École Polytechnique, the elite engineering school in Paris, and then served as a military engineer, though by most accounts his military career was unremarkable. What consumed Carnot's imagination wasn't warfare. It was steam engines. And specifically, it was a question that bothered him deeply. France was falling behind Britain in industrial power, and Carnot believed this was partly because the French didn't understand the fundamental principles governing heat engines. The British had better engines, yes, but they'd arrived at them through practical tinkering, through trial and error, through the Watts and Boltons of the world. Carnot wanted to find the theory. He wanted to know, what is the maximum possible efficiency of a heat engine? Not a particular engine, not Watt's engine or anyone else's engine, but any engine, the best engine that could ever theoretically exist. And in 1824, at the age of just 28, he published a slim book called Reflections on the Motive Power of Fire. It's one of those works that almost nobody read when it came out. It sold poorly. It was largely ignored by the scientific establishment. Carnot himself died just 8 years later, in 1832, during a cholera epidemic in Paris. He was 36 years old. Most of his papers were burned after his death, as was the custom during cholera outbreaks to prevent the spread of disease. Think about that. We'll never know what else he was working on, what other insights he might have had. But that one little book, that one book contained ideas so profound that when they were finally rediscovered and understood, they became the foundation of the second law of thermodynamics. And here's what Carnot figured out, and I want you to really sit with this because it's one of those ideas that seems simple on the surface, but gets deeper the longer you think about it. Carnot imagined an ideal engine, a perfect engine with no friction, no heat leaks, no wasted energy of any kind. And he asked, even in this perfect case, is there a limit to how much work you can extract from a given amount of heat? His answer was yes. And the limit depends on only one thing: the temperature, difference between the hot source providing the heat and the cold sink absorbing the waste heat. That's it. Not the working fluid, not the design of the engine, not the materials, not the cleverness of the engineer, just the temperatures. He drew an analogy to a waterfall. A waterfall can drive a water wheel, and the amount of work you can extract depends on how far the water falls, the height difference. Similarly, Carnot argued, heat falls from a high temperature to a low temperature, and the amount of work you can extract depends on that temperature difference. The greater the difference between your hot source and your cold sink, the more efficient your engine can be. But, and this is the crucial part, you can never convert all of the heat into work. Some heat must always be rejected to the cold sink. Always. No matter how perfect your engine is. Now, Carnot was actually wrong about one important thing. He still believed in caloric theory, the idea that heat was a substance, a fluid that was conserved, that flowed from hot to cold, but was never created or destroyed. That theory was already on shaky ground, and within a few decades, it would be completely overthrown. But here's what's remarkable. Carnot's conclusions were right, even though his reasoning was based on a flawed model. The maximum efficiency he calculated, the idea that waste heat is unavoidable, the dependence on temperature difference, all of that survived the death of caloric theory and remains true today. It's as if someone navigated perfectly to a destination using a map that had the wrong continent shapes but the right compass bearings. And that result, that you can never convert heat entirely into work, that there's always waste, always a tax the universe collects. That's going to become the second law of thermodynamics. But we're getting slightly ahead of ourselves, because before the second law could be properly stated, someone had to first nail down the first law. Someone had to finally answer the question that had been lingering since the ancient Greeks. Is heat a substance, or is it something else entirely? And the person who drove the final nail into the coffin of caloric theory was, of all people, a brewer's son from Salford, England, a man with no university degree and no academic position, working in his family's brewery with equipment he built himself. His name was James Prescott Joule, and what he was about to demonstrate, with an almost obsessive precision that bordered on the eccentric, was that heat and mechanical work were two forms of the same thing, that they were interchangeable, that you could convert one into the other at a fixed, measurable rate, and that rate never changed, not depending on the material, not depending on the method, not depending on anything at all. It was a universal constant, hiding in plain sight, and Joule spent the better part of 2 decades proving it with experiment after painstaking experiment until the scientific establishment had no choice but to listen. Now, Joule's background is important here, because it shaped everything about how he worked. He was born in 1818 into a wealthy brewing family in Salford, just outside Manchester, right in the beating heart of industrial England. His father owned a successful brewery, and young James was educated privately, tutored at home for a while. And then, for a brief and formative period, he and his brother studied under John Dalton. Yes, that John Dalton, the chemist who gave us modern atomic theory. Dalton was elderly by then, but he taught the Joule brothers arithmetic, geometry, and chemistry, and more importantly, he instilled in James a deep respect for careful measurement. Dalton was a meticulous observer of nature. He kept weather records every single day for decades, and that habit of mind, that reverence for precision, clearly rubbed off on his young student. Joule never went to university. He never held an academic position. He worked in the family brewery, and he did his experiments in a laboratory he set up himself, initially right there in the brewery, using equipment he designed and often built with his own hands. And this is part of what makes his story so compelling. He was an outsider, a gentleman amateur in an era when that was still possible but increasingly unusual. The scientific establishment in Britain was centered on places like Cambridge and the Royal Society. And here was this brewer from Manchester sending in papers about the mechanical equivalent of heat. It took a long time for them to take him seriously. His early work, in the late 1830s and early 1840s, focused on electric motors and the relationship between electricity and heat. He was interested in whether electric motors could replace steam engines, a practical question for a brewer, and in the process, he started noticing something. When you ran current through a wire, it got hot. The amount of heat produced was related to the current and the resistance in a very precise way. He published what we now call Joule's first law. The heat produced by an electric current is proportional to the square of the current multiplied by the resistance, in 1841, when he was just 22 years old. But what really caught his attention was the bigger implication. The electrical energy was being converted into heat, not heat flowing from somewhere else, not caloric fluid being squeezed out. The energy of the current was becoming heat. They were the same kind of thing. This was a radical idea. Under caloric theory, heat was a conserved substance. You couldn't create it or destroy it, only move it around. But Joule was watching heat appear out of electrical work, and the amount of heat was precisely proportional to the amount of work done. So he started asking, is this true for all kinds of work? Not just electrical, but mechanical. If you stir water, does the friction create heat? And if so, how much work produces how much heat? Is there a fixed conversion rate? And this is where the famous paddle wheel experiment comes in. You've probably heard of it. It's one of those iconic experiments in the history of science, like Galileo dropping things from the Tower of Pisa, except Joule's actually happened. Here's how it worked. Imagine an insulated container of water. Joule used a brass vessel, carefully designed to minimize heat loss to the surroundings. Inside the water, there's a set of paddle wheels, like little fins or vanes attached to a central shaft. The paddles can spin freely inside the water, but the container also has fixed vanes attached to the walls, so when the paddles turn, the water can't just spin along with them. It gets churned and agitated. There's friction between the moving water and the fixed vanes, and that friction generates heat. Now here's the clever part. The paddle wheel shaft goes up through the top of the container, and it's connected by strings and pulleys to a pair of lead weights. The weights hang on either side, and when you release them, gravity pulls them down. The strings turn the shaft, the paddles spin in the water, and the water gets very slightly warmer. Joule measured the temperature change with extraordinary precision. We're talking about fractions of a degree Fahrenheit. He used thermometers that he had calibrated himself, thermometers that could detect changes as small as 1/200th of a degree. For the 1840s, this was astonishing precision. Most scientists of the era wouldn't have believed such small temperature changes could be reliably measured. And Joule ran this experiment over and over. He varied the weight. He varied the height the weights fell. He measured the temperature rise each time, and what he found was beautifully consistent. The amount of heat produced in the water was directly proportional to the mechanical work done by the falling weights. Every time, the ratio was constant. He could calculate exactly how many foot-pounds of work it took to raise the temperature of 1 pound of water by 1 degree Fahrenheit. The number he arrived at, after years of refinement, was approximately 772 foot-pounds per British thermal unit. In modern metric terms, that's about 4.2 joules per calorie. And yes, the unit of energy is named after him, which tells you something about how important this turned out to be. But here's the thing. When Joule first presented these results, almost nobody cared. He read a paper to the British Association for the Advancement of Science in 1843, and it was met with polite indifference. He submitted papers to the Royal Society, and they were essentially ignored. The scientific establishment wasn't ready. Caloric theory was deeply entrenched. The idea that heat was a substance had been the working model for decades, and it explained a lot of phenomena reasonably well. And here was this unknown brewer from Manchester claiming he could create heat from mechanical work at a fixed rate, which meant heat wasn't a substance at all, but a form of energy. It was too much, too fast, from too unlikely a source. Joule kept at it. He didn't just do the paddle wheel experiment. He measured the heat produced by compressing gases, by forcing water through narrow tubes, by all sorts of mechanical processes. And every single time, he got the same conversion factor. The number was always the same. That consistency was his strongest argument, and he knew it. He was building an overwhelming case, brick by brick, experiment by experiment. The turning point came in 1847 at a meeting of the British Association in Oxford. Joule presented his results yet again, and this time, a young man in the audience stood up and asked sharp, probing questions. That young man was William Thomson, later Lord Kelvin, who was only 23 years old at the time, but already a professor of natural philosophy at the University of Glasgow. Thomson was initially skeptical, but he was also brilliant enough to recognize the significance of what Joule was claiming. The two struck up a correspondence and eventually a friendship that would last decades and prove enormously productive for both of them. Thomson's interest gave Joule credibility. Here was a Cambridge-educated, mathematically sophisticated physicist taking the brewer's experiments seriously. And Thomson himself was grappling with exactly these questions. He'd been studying Carnot's work, trying to reconcile Carnot's insights about engine efficiency with the growing evidence that heat could be created and destroyed. Because if Joule was right, and heat was just a form of energy that could be converted from mechanical work, then caloric theory was dead. Heat wasn't conserved. And if heat wasn't conserved, then what was Carnot's theory actually resting on? This was a genuine intellectual crisis, and Thomson felt it acutely. He spent years trying to reconcile the two. Carnot said heat flowed from hot to cold, and in doing so produced work, like water flowing downhill turning a mill wheel. Joule said heat could be created from work and destroyed by converting it back to work. Both couldn't be entirely right under the old framework. Something had to give. And this is where another figure enters the story, a man who doesn't get nearly enough credit in the popular telling of thermodynamics, though he arguably deserves more than almost anyone. His name was Rudolf Clausius, and he was a German physicist working in Berlin, and in 1850 he published a paper that essentially resolved the whole mess. Clausius realized that you could keep the core of Carnot's insight, the part about efficiency depending on temperature difference, the part about waste heat being unavoidable, while throwing out the caloric theory underneath it. You just had to replace the idea of heat conservation with energy conservation. Heat wasn't a substance that was preserved. Energy was the thing that was preserved, and heat was one form it could take. Work was another. You could convert between them, just as Joule had shown, but the total energy was always conserved. This was the first law of thermodynamics, stated clearly for the first time. Energy cannot be created or destroyed, only transformed from one form to another. The total energy of an isolated system is constant, and it sounds simple when you say it like that, almost obvious even. But think about what it took to get there. Centuries of confusion about the nature of heat, decades of careful experiments, the overthrow of a theory that had dominated physics for 100 years, and the synthesis of two seemingly contradictory sets of results, Carnot's and Joule's, into a single coherent framework. Clausius didn't stop there, though. In that same 1850 paper, he also began to formalize what would become the second law. He stated it in a deceptively simple way. Heat cannot spontaneously flow from a colder body to a warmer one. That's it. That's the second law in its earliest form. It sounds almost trivially obvious. Of course, hot things warm up cold things, not the other way around. You've never seen an ice cube heat up a cup of coffee. But the implications of that simple statement are staggering, and Clausius would spend the next 15 years unpacking them, developing a concept that would become one of the most profound and misunderstood ideas in all of science. He would eventually give it a name, a word he deliberately coined from Greek roots to sound like energy, because he felt the concept was equally fundamental. He called it entropy. And that word, entropy, would go on to become one of the most powerful, most debated, and most beautifully strange ideas in the history of human thought. But let's not rush past the moment. Let's sit with it for a second, because the way Clausius arrived at this concept is itself a story worth savoring. See, Clausius knew that the first law, energy conservation, was necessary but not sufficient to describe how the world actually works. The first law tells you that energy is always conserved, that it can't be created or destroyed. Fine. But it doesn't tell you which direction things go. It doesn't tell you why heat flows from hot to cold, and not the other way around. Mathematically, the first law would be perfectly happy if heat flowed from your cold hands into a hot stove, warming the stove further while your hands got even colder. The energy books would balance just fine. But that never happens. There's a directionality to nature, an arrow that points one way, and the first law alone can't explain it. Something else is going on, something deeper. And Clausius spent years trying to figure out exactly what that something was and how to express it mathematically. He started by thinking carefully about what happens inside a heat engine, going back to Carnot's analysis, which he'd already rescued from the wreckage of caloric theory. In an ideal Carnot engine, you take in heat from a hot reservoir, convert some of it to work, and dump the rest into a cold reservoir. And Carnot had shown that the efficiency of this process depends only on the temperatures of the two reservoirs. But Clausius pushed further. He asked, what quantity is it exactly that remains balanced in a perfectly reversible cycle? Not energy. Energy is always conserved in every process, reversible or not. No, there was something else, some other quantity that stayed constant in a perfect cycle, but increased in every real, irreversible process. And this is where the mathematics led him somewhere genuinely new. He defined a quantity, the heat transferred divided by the temperature at which the transfer occurs. If you add a small amount of heat to a system at a high temperature, this ratio is small. If you add the same amount of heat at a low temperature, the ratio is larger. And what Clausius discovered is that for a perfectly reversible cycle, an ideal Carnot engine running with no friction, no waste, no irreversibility of any kind, the sum of all these little ratios around the entire cycle adds up to exactly zero. Heat divided by temperature, summed all the way around, equals zero. But for any real process, any process that involves friction or turbulence or heat flowing across a finite temperature difference, the sum is always greater than zero. Always. Without exception. This was entropy, the quantity that Clausius defined as heat divided by temperature, tracked through a process, and it had this remarkable property. In any real process, in any spontaneous change, entropy always increases. It never decreases. You can hold it constant if you're incredibly careful and everything is perfectly reversible, but you can never, ever make it go down in an isolated system. And this is the second law of thermodynamics in its most precise form. Not just heat flows from hot to cold. That's a consequence. The deeper truth is that entropy always increases. The total entropy of the universe is always going up. Now, here's the thing about entropy that makes it so fascinating and so frustrating at the same time. It's not like energy, which you can sort of feel intuitively. You know what it means for something to have a lot of energy. It's moving fast, or it's hot, or it's high up. Energy feels concrete. Entropy is more elusive. Clausius himself described it as the transformation content of a system, the Verwandlungsinhalt in German, which gives you a sense of what he was reaching for. It's a measure of how much transformation has occurred, how much of the system's energy has been spread out and dispersed in ways that can't be easily gathered back up. Think about it this way. If you have a hot cup of coffee in a cold room, there's a temperature difference, and that difference is useful. You could, in principle, run a tiny heat engine between the coffee and the room and extract some work. But as the coffee cools and the room warms up ever so slightly, that temperature difference shrinks and your ability to extract work diminishes. Eventually, the coffee reaches room temperature and you've got nothing. The energy is still there, every last joule of it, but it's spread out uniformly and it's useless. That spreading out, that transition from concentrated, useful energy to dispersed, useless energy, that's entropy increasing. Clausius published his most complete formulation in 1865, and he summarized the two laws of thermodynamics in a pair of statements that are still quoted today. He wrote, Die Energie der Welt ist konstant. Die Entropie der Welt strebt einem Maximum zu. The energy of the universe is constant. The entropy of the universe tends toward a maximum. 2 sentences. That's the whole game. Everything that happens, every process in nature, every chemical reaction, every living thing growing and dying, every star burning and cooling, all of it is the universe conserving its energy while its entropy climbs relentlessly upward. And you might be lying there thinking, okay, that's philosophically interesting, but does it actually matter for engineering? And the answer is, it matters enormously. It matters more than almost anything else in engineering, because the second law is what sets the fundamental limits on what any machine can do. It's the reason you can't build a perfect engine. It's the reason power plants need cooling towers. It's the reason your car's engine gets hot and needs a radiator. Every engineer who designs anything that converts energy from one form to another is wrestling with entropy, whether they know it or not. But let's come back to the human story, because while Clausius was developing these ideas in Zurich and later in Bonn, something remarkable was happening across the English Channel. William Thomson, Lord Kelvin as he'd become, was working on these same problems, and the intellectual relationship between Thomson and Clausius is one of those fascinating dynamics where two brilliant minds are circling the same truth from different directions, sometimes cooperating, sometimes competing, occasionally stepping on each other's toes. Thomson had his own version of the second law, stated independently around the same time as Clausius. His version said, "It is impossible to construct a device that operates in a cycle and produces no effect other than the extraction of heat from a single reservoir and the performance of an equivalent amount of work. In plain language, you can't build an engine that converts heat entirely into work with no waste. There must always be some heat rejected to a cold reservoir." This sounds different from Clausius's version. Clausius talked about heat not flowing spontaneously from cold to hot. Thomson talked about not being able to convert heat entirely to work. But they're mathematically equivalent. If you could violate one, you could violate the other. They're two faces of the same deep truth. And Thomson contributed something else that was absolutely crucial: the absolute temperature scale. Remember how Carnot had shown that engine efficiency depends on the temperature difference between the hot and cold reservoirs? Well, that only works cleanly if you measure temperature on a scale that starts at a true zero. Not the 0 of Celsius, which is just where water happens to freeze, but a 0 that means genuinely no thermal energy at all. Thomson proposed this in 1848, and we still call it the Kelvin scale in his honor. 0 Kelvin, about minus 273 degrees Celsius, is absolute zero, the point where, in classical terms, all molecular motion ceases. You can't get colder than that, and with this scale in hand, Carnot's efficiency formula becomes beautifully clean. The maximum efficiency of any heat engine is 1 minus the cold temperature divided by the hot temperature, both measured in kelvins. So if your hot reservoir is at 600 Kelvin and your cold reservoir is at 300 Kelvin, the best you can possibly do is 50% efficiency. Not because of bad engineering, not because of friction or poor design, because the universe itself forbids you from doing better. That's the second law, expressed as a hard mathematical ceiling. Now, while Clausius and Thomson were formalizing these grand laws, a young Scotsman was about to enter the picture and transform the entire field in a way that neither of them could have anticipated. His name was James Clerk Maxwell, and if you know that name, it's probably because of electromagnetism. Maxwell's equations, the unification of electricity and magnetism, the prediction of electromagnetic waves. That alone would make him one of the greatest physicists who ever lived. But Maxwell also made a contribution to thermodynamics that was, in its own way, just as revolutionary. Because Maxwell started asking a question that Clausius and Thomson had carefully avoided. What is heat, actually, at the microscopic level? What's really going on down there among the atoms and molecules? By the late 1850s, the atomic theory of matter was gaining ground but was still controversial. Many physicists, including some very prominent ones, didn't believe atoms were real. They thought atoms were a useful fiction, a calculational convenience, nothing more. But Maxwell took atoms seriously, and in 1859, he published a paper that would lay the groundwork for an entirely new way of understanding thermodynamics. He asked, if a gas is really made of billions of tiny particles bouncing around and colliding with each other and with the walls of their container, what can you say about how fast those particles are moving? Not any individual particle, that would be hopeless to track, but the statistical distribution of speeds across the whole population. And here's what's really clever about what Maxwell did. He didn't try to solve the impossible problem of tracking every single molecule. Instead, he borrowed ideas from probability theory, from the mathematics of chance and statistics, and applied them to physics. He derived what we now call the Maxwell distribution of molecular speeds, and it tells you something beautiful. In a gas at a given temperature, the molecules aren't all moving at the same speed. Some are crawling along, some are zipping around at tremendous velocity, and most are somewhere in the middle. The distribution has a characteristic shape. It rises, peaks, and then tails off, and the peak shifts to higher speeds as you raise the temperature. Temperature, in this picture, isn't some mysterious fluid or even an abstract thermodynamic quantity. Temperature is directly related to the average kinetic energy of the molecules. Hot means the molecules are moving fast. Cold means they're moving slow. That's it. That's what temperature is. This was the birth of what we now call statistical mechanics, and it would eventually provide a microscopic foundation for everything Clausius and Thomson had built. But it also raised a deeply troubling question, a question that Maxwell himself posed in the form of a famous thought experiment that would haunt physicists for over a century. He imagined a tiny, intelligent being, later dubbed Maxwell's demon by Thomson, stationed at a small door between two chambers of gas at the same temperature. This little creature could observe individual molecules approaching the door and selectively open it to let fast molecules through in one direction and slow molecules through in the other. Over time, one chamber would get hotter and the other cooler, without any work being done. Heat would flow from cold to hot. Entropy would decrease. The second law would be violated. And that's the puzzle. That's the thing that kept people up at night. Because Maxwell wasn't saying the second law was wrong. He was saying something much more subtle. He was asking whether the second law is truly fundamental, truly absolute, or whether it's something else entirely. Whether it's a statement about probability rather than certainty. And here's the thing. Maxwell himself seemed to lean toward that second interpretation. He suspected, even as early as the 1860s, that the second law of thermodynamics is not like the laws of mechanics. It's not a hard, unbreakable rule carved into the fabric of the universe the way Newton's laws appear to be. It's a statistical truth. It holds because there are so astronomically many molecules in any real sample of gas that the odds of them spontaneously sorting themselves, fast ones here, slow ones there, are so vanishingly small as to be, for all practical purposes, zero. But not absolutely zero. Not impossible. Just overwhelmingly, crushingly unlikely. The second law, in this view, is the most reliable bet you will ever make, but it's still a bet. Now, that might sound like a subtle, philosophical distinction, and in one sense, it is. But it matters. It matters because it changes what entropy means at the deepest level. And the person who would make that change most explicit, who would write down the equation that connects entropy to probability in a way so clean and so powerful that it's literally carved on his tombstone, that person was Ludwig Boltzmann. Boltzmann was Austrian, born in Vienna in 1844, and he was brilliant in that restless, tormented way that seems to characterize so many of the great physicists of that era. He studied under Joseph Stephan, who you might recognize from the Stefan-Boltzmann law of thermal radiation, and he threw himself into the kinetic theory of gases with an intensity that bordered on obsession. Where Maxwell had laid the statistical groundwork, Boltzmann wanted to build the entire edifice. He wanted to derive the second law of thermodynamics, entropy increase, the arrow of time, all of it, from the mechanics of molecules and the mathematics of probability. And he largely succeeded, though the fight to get people to accept what he'd done nearly destroyed him. Let's talk about what Boltzmann actually did, because it's genuinely one of the most beautiful ideas in all of physics. Start with a simple question. If you have a box full of gas molecules bouncing around, how many different ways can those molecules be arranged? And by arranged, I mean, what are all the possible combinations of positions and velocities that the molecules could have? Each specific arrangement is called a microstate. Every single detailed configuration of every single molecule, where it is, how fast it's going, in what direction. That's one microstate. Now here's the key insight. Many different microstates can correspond to the same macrostate. A macrostate is what you actually observe at the human scale, the temperature, the pressure, the volume, the density. You can measure those things with a thermometer and a pressure gauge. You can't see the individual molecules. So a macrostate is like a summary, and a microstate is the full detailed story underneath. Think of it this way. Imagine you have a jar of coins, say 100 coins, and you shake the jar and dump them out. The macrostate might be something like 60 heads and 40 tails. But there are an enormous number of different specific arrangements of individual coins that give you 60 heads and 40 tails. Each specific arrangement, coin 1 is heads, coin 2 is tails, coin 3 is heads, and so on. That's a microstate. And the macrostate 50 heads, 50 tails has vastly more microstates than 99 heads, 1 tail, because there are just so many more ways to get a roughly even split than a lopsided one. Boltzmann's great leap was to say, entropy is a measure of how many microstates correspond to a given macrostate. High entropy means there are an enormous number of microscopic arrangements that all look the same from the outside. Low entropy means there are relatively few. And the second law, the tendency of entropy to increase, is simply the statement that systems tend to evolve from less probable macrostates to more probable ones. Not because there's some mysterious force pushing them there. just because there are overwhelmingly more ways to be in a high entropy state than a low entropy one. It's like asking why, if you shuffle a deck of cards, you don't end up with them perfectly sorted by suit and number. You could. There's nothing in the laws of physics preventing it. It's just that there's exactly one arrangement that counts as perfectly sorted and an astronomical number that count as shuffled. So you get shuffled. Every time. The equation Boltzmann wrote down to capture this is S equals K log W. S is entropy. W is the number of microstates, the number of ways the microscopic details can be arranged while still producing the same macroscopic appearance. And K is a constant, now called Boltzmann's constant, that bridges the microscopic world of molecules to the macroscopic world of thermometers and engines. It's a tiny number, about 1.38 times 10 to the negative 23 joules per Kelvin, and it tells you the scale at which molecular chaos becomes thermodynamic behavior. That equation is on his gravestone in Vienna. If you ever visit the Zentralfriedhof, the great central cemetery there, you can find it. S equals K log W. It might be the most profound equation in all of thermodynamics. But here's the thing. Not everyone was convinced. In fact, Boltzmann faced fierce opposition, and the arguments against him were not stupid. They were serious, and they came from serious people. The most famous objection is called the reversibility paradox, or Loschmidt's paradox, after Boltzmann's colleague Joseph Loschmidt. The argument goes like this. The laws of mechanics, Newton's laws, the equations governing how molecules bounce off each other, are time reversible. If you filmed a collision between two molecules and played the film backward, the reversed collision would also be a perfectly valid solution of Newton's laws. There's nothing in the microscopic physics that distinguishes past from future. So how can you derive an irreversible law, the second law, which says entropy always increases, which gives time a direction, from reversible underlying mechanics? How do you get a one-way street from laws that work equally well in both directions? It's a genuinely deep question, and Boltzmann's answer was subtle and, honestly, not fully appreciated in his own lifetime. He argued that the second law is not a mechanical law, but a statistical one. It doesn't say entropy must increase in every single case. It says entropy is overwhelmingly likely to increase because the number of high-entropy microstates so vastly outnumbers the number of low-entropy ones. In principle, entropy could decrease. Molecules could spontaneously sort themselves. A broken egg could reassemble. It's just that you'd have to wait longer than the age of the universe for it to happen, and even then you'd probably be disappointed. There was another objection too, called the recurrence paradox, based on a mathematical theorem by Henri Poincaré. Poincaré had proved that any mechanical system confined to a finite space will, given enough time, return arbitrarily close to its initial state. So if you start with low entropy, wait long enough, and the system must eventually return to low entropy. Entropy can't just increase forever. Boltzmann's response was essentially the same. Yes, recurrence will happen, but the timescale is so absurdly, incomprehensibly long that it has no practical relevance whatsoever. For any real system, in any real time frame, entropy increases. The statistics are just that overwhelming. Now, all of this was happening in the latter decades of the 19th century, and you have to understand the intellectual climate. There was a significant school of thought, led by thinkers like Ernst Mach and Wilhelm Ostwald, that rejected the very existence of atoms. They thought atoms were a useful fiction, a calculational tool, but not real physical entities. And if atoms aren't real, then Boltzmann's entire program, deriving thermodynamics from the statistics of molecular motion, is built on sand. Mach was particularly cutting. He reportedly asked Boltzmann during a lecture, "Have you ever seen one?" Meaning an atom. It sounds almost quaint now, in an age when we can literally image individual atoms with scanning tunneling microscopes, but at the time, it was a serious challenge. Nobody had directly observed an atom. The evidence was indirect: gas laws, chemical combining ratios, kinetic theory predictions, and for a strict empiricist like Mach, that wasn't enough. Boltzmann fought this battle for decades, and it wore him down. He was prone to depression, what we would now probably diagnose as bipolar disorder, and the relentless intellectual opposition took a terrible toll. He felt increasingly isolated, increasingly convinced that his life's work was being rejected. In September of 1906, while on vacation with his family near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. It's one of the saddest stories in the history of physics, made all the more tragic by the fact that vindication was already on its way. Just the year before, in 1905, a young patent clerk in Bern named Albert Einstein had published a paper on Brownian motion, the random jiggling of tiny particles suspended in a fluid, showing that it could be quantitatively explained by molecular bombardment. It was, in effect, proof that atoms were real. And within a few years, the experimental physicist Jean Perrin would confirm Einstein's predictions with meticulous experiments, earning a Nobel Prize for his trouble. Boltzmann was right. Atoms are real, statistical, mechanics works, and S equals K log W is one of the truest things anyone has ever written down. But let's come back to Maxwell's demon for a moment, because the resolution of that puzzle turns out to connect thermodynamics to something you might not expect: information. Remember the setup: a tiny creature sorting fast and slow molecules to decrease entropy without doing work. For decades, people tried to find the flaw. In 1929, the Hungarian physicist Leo Szilard took a major step, arguing that the demon's act of measurement, of observing each molecule to determine whether it's fast or slow, must itself involve a thermodynamic cost. The demon has to acquire information, and acquiring information isn't free. Then, much later, in 1961, Rolf Landauer at IBM made an even more precise argument. Landauer showed that it's not the measurement that necessarily costs energy, it's the erasure of information. The demon has a finite memory. Eventually, it has to erase old measurements to make room for new ones, and Landauer proved that erasing one bit of information must dissipate a minimum amount of energy as heat, specifically kT times the natural log of 2, where T is the temperature. That tiny, irreducible energy cost is enough to save the second law. The entropy, decrease the demon creates by sorting molecules, is exactly compensated by the entropy increase from erasing information in its memory. Think about what that means. It means information is physical. Erasing a bit of data has a real measurable thermodynamic cost. It connects the abstract world of information and computation to the concrete world of heat and energy. And it means that every computer you've ever used, every processor crunching numbers in your phone right now, is fundamentally a thermodynamic engine. Every time it clears a register, every time it overwrites a memory cell, it generates a tiny amount of waste heat that cannot be eliminated even in principle. That's not an engineering limitation. It's a law of nature, Landauer's principle. And it all traces back to a thought experiment about a tiny demon that Maxwell dreamed up in the 1860s. So by the end of the 19th century, thermodynamics had been transformed. What started as a practical science of steam engines had become something much deeper, a framework connecting energy, entropy, probability, atoms, and even information. But there was still one enormous puzzle waiting, one that would crack open an entirely new era of physics. And it started, as so many things in thermodynamics do, with a seemingly simple question about heat. This time, the question was about the light emitted by hot objects, the warm glow of a furnace, the red shimmer of heated iron, the white brilliance of the sun itself. Every hot object glows, and by the late 1800s, physicists had gotten very good at measuring exactly how much light comes out at each wavelength, how much red, how much blue, how much invisible infrared. They'd built special experimental cavities, essentially hollow enclosures with a tiny hole, heated to precise temperatures, and they'd carefully cataloged the spectrum of light pouring out. This setup had a name, a blackbody radiator, and the spectrum it produced was beautifully smooth, a single hump that shifted depending on temperature. Heat the cavity to a dull red glow, and the peak of the hump sits in the infrared, with just a bit of visible red light trailing off the edge. Heat it more, and the peak moves toward orange, then yellow, then blue-white. The hotter the object, the shorter the wavelength at the peak. That relationship had actually been nailed down quantitatively by Wilhelm Wien in 1893, Wien's displacement law it's called, and it matched the experiments beautifully on the short wavelength side of the hump. But here's where things started going wrong. On the other side of the hump, the long wavelength side, the infrared tail, Wien's formula didn't quite work. And meanwhile, two British physicists, Lord Rayleigh and James Jeans, had tried to derive the black-body spectrum from first principles using classical physics, using the well-established laws of thermodynamics and electromagnetism that everyone trusted. And they got a formula that worked reasonably well for long wavelengths, but did something absolutely catastrophic at short wavelengths. Their formula predicted that as you moved toward shorter and shorter wavelengths, toward the ultraviolet and beyond, the amount of energy radiated should increase without limit. It should just keep climbing forever toward infinity, which would mean that every hot object in the universe should be radiating infinite energy, mostly in the ultraviolet. Obviously, that doesn't happen. Your coffee mug is not bathing you in lethal gamma rays. This spectacular failure got a dramatic name, the ultraviolet catastrophe, and it wasn't just a minor discrepancy. It was classical physics contradicting itself in the most fundamental way possible. The math was correct, the assumptions were standard, and the answer was nonsense. Now, this is October 1900, and a German physicist named Max Planck is staring at this problem. Planck was 42 years old, a professor in Berlin, meticulous, conservative by temperament, deeply committed to classical thermodynamics. He was not a revolutionary by nature. He was the kind of physicist who wanted everything tidy and well-founded, and yet he was about to do something that would shatter the foundations of physics, almost against his own will. Planck had been working on the blackbody problem for years. He'd been trying to derive the correct spectrum using thermodynamic reasoning, and he'd gotten tantalizingly close. He knew what the right curve looked like. The experimentalists had measured it precisely, and he'd actually managed to write down a formula that fit the data perfectly across all wavelengths. He presented it on October 19th, 1900, at a meeting of the German Physical Society. The formula worked. It matched every measurement. But there was a problem. He'd essentially guessed it. He'd interpolated between Wien's formula, which worked at short wavelengths, and the Rayleigh-Jeans formula, which worked at long wavelengths, and found a mathematical expression that bridged the two. It was a brilliant piece of curve fitting, but it wasn't derived from any physical principle. Planck didn't know why it worked, and that bothered him enormously. So over the next 2 months, he worked furiously to find a theoretical justification for his formula. And in December 1900, December 14th to be precise, a date that many physicists consider the birthday of quantum theory, he presented his derivation. And here's what he had to assume to make it work. He had to assume that the tiny oscillators in the walls of the blackbody cavity, the vibrating charges that emit and absorb light, could not take on any arbitrary amount of energy. Instead, they could only have energies that came in discrete chunks, specific, indivisible packets. He called these packets quanta, from the Latin word for how much, and the size of each quantum was proportional to the frequency of the oscillation. Higher frequency, bigger quantum. The constant of proportionality was a new fundamental constant that Planck introduced. We now call it Planck's constant, h, and it's a tiny, tiny number, about 6.6 times 10 to the negative 34 joule seconds. Here's the thing. This assumption was completely at odds with classical physics. In the classical world, energy is continuous. An oscillator can vibrate with any amplitude, carry any amount of energy, smoothly and without restriction. Planck was saying no, energy comes in lumps. And the reason this fixes the ultraviolet catastrophe is subtle but beautiful. Think about it this way. At any given temperature, the thermal energy available is roughly K times T, Boltzmann's constant times the temperature. That's the typical energy scale of thermal fluctuations. Now, for low-frequency oscillators, the quantum of energy, h times the frequency, is very small compared to kT, so those oscillators can easily absorb and emit quanta. They behave almost classically, and they contribute to the spectrum roughly the way Rayleigh and Jeans predicted. But for high-frequency oscillators, the ones that were causing the ultraviolet catastrophe, the quantum of energy is much larger than kT. It's like asking a thermal fluctuation to cough up a huge amount of energy all at once. And statistically, that almost never happens. So those high-frequency modes are effectively frozen out. They can't participate. And that's what kills the ultraviolet catastrophe. The energy doesn't climb to infinity at short wavelengths because the quantum toll booth is too expensive for high-frequency oscillators to pass through at any given temperature. And notice how Boltzmann's statistical mechanics is woven right into this. Planck actually used Boltzmann's entropy formula, S equals K log W, in his derivation. He counted the number of ways to distribute energy quanta among oscillators, exactly the kind of combinatorial counting that Boltzmann had pioneered. It's deeply ironic, because Planck had actually been somewhat skeptical of Boltzmann's statistical approach. He'd preferred a more classical, continuous thermodynamics. But when he needed to derive the blackbody spectrum, Boltzmann's methods were the only ones that worked. Planck later called his quantum hypothesis an act of desperation. He didn't really believe energy was fundamentally quantized. He thought it was a mathematical trick, a provisional assumption that would eventually be explained away by some deeper classical theory. He spent years trying to undo what he'd done, trying to find a way to get the same result without the quantum assumption. He never succeeded, but others took the idea and ran with it. And the first person to really take quanta seriously, to treat them not as a mathematical convenience but as a physical reality, was, of course, Albert Einstein. In 1905, the same miraculous year he published his work on Brownian motion that would vindicate Boltzmann's atoms, Einstein published a paper on the photoelectric effect that extended Planck's idea in a radical direction. Planck had quantized the energy of oscillators, the the things emitting and absorbing light. Einstein went further. He proposed that light itself comes in quanta, that a beam of light is not a continuous wave, but a stream of discrete energy packets, each carrying energy equal to h times the frequency. We call them photons now, though that name came later. The photoelectric effect was the evidence. When you shine light on a metal surface, electrons get knocked loose. But the strange thing was, the energy of the ejected electrons didn't depend on the brightness of the light. It depended on the color, on the frequency. Dim ultraviolet light would eject energetic electrons, but even blindingly bright red light wouldn't eject any electrons at all if the frequency was too low. Classical wave theory couldn't explain this, but Einstein's photon idea explained it perfectly. Each photon carries a fixed amount of energy determined by its frequency. If that energy is enough to overcome the binding energy holding the electron in the metal, the electron pops out. If not, nothing happens, no matter how many low-energy photons you throw at it. It's like trying to knock down a door. 1,000 gentle pushes won't do what one solid kick will. Einstein's photoelectric paper won him the Nobel Prize in 1921. Not relativity, not Brownian motion, but this, the quantum of light. And it was thermodynamics, the black-body problem, that opened the door. Now, there's something poetic about the timeline here. Boltzmann died in September 1906, likely never knowing that his statistical methods had just been used to crack open an entirely new physics. Planck's quantum hypothesis relied on counting microstates, on treating energy as something that could be distributed in discrete, countable units among oscillators. That's pure Boltzmann. The man whose ideas were attacked and dismissed by the scientific establishment, whose statistical interpretation of entropy was called meaningless by Mach and unnecessary by Ostwald, his framework turned out to be not just correct, but indispensable for the quantum revolution. The formula on his tombstone, S equals Ka log W, is carved into the very foundations of modern physics, and the quantum revolution, once it started, transformed thermodynamics yet again. Because now you had to think about energy levels, about discrete states, about the statistical mechanics of systems where the old continuous assumptions didn't hold. In the years that followed, Einstein applied quantum ideas to the specific heat of solids. Remember specific heat, that concept Joseph Black had carefully measured back in the 1760s, and solved a puzzle that had nagged physicists for decades. Classical theory predicted that all crystalline solids should have the same specific heat at all temperatures, about 3 times Boltzmann's constant per atom. And at room temperature, that prediction worked pretty well. But as you cooled materials down toward absolute zero, their specific heats dropped, approaching zero. Classical physics had no explanation for this. Einstein, in 1907, modeled the atoms in a solid as quantum oscillators, each vibrating at a single frequency with quantized energy levels, and showed that at low temperatures, the energy quanta become too large for thermal fluctuations to excite, so the oscillators freeze out, exactly the same logic that solved the black-body problem. The specific heat drops because the atoms can't absorb energy in small enough increments. Peter Debye refined the model in 1912 by allowing a spectrum of vibration frequencies rather than just one, and his theory matched experiments beautifully. So here's thermodynamics, reaching back to its own past and resolving old mysteries with new tools. Black's careful measurements of how much heat it takes to warm different substances, Joule's precise experiments connecting work and heat, Boltzmann's statistical counting of microstates, all of it converging in the early 20th century into a quantum statistical mechanics that explained things the founders of the field could never have imagined. And this quantum thermodynamics had practical consequences that would reshape the 20th century. Understanding how electrons occupy energy levels in solids, how they obey quantum statistics, specifically the Fermi-Dirac statistics worked out in the mid-1920s, led directly to the theory of semiconductors, and semiconductors led to transistors, and transistors led to everything. Every device you're using, every screen you've ever stared at, every phone call, every photograph taken on a digital camera, every medical scan, every satellite signal, all of it traces back through an unbroken chain of ideas to people trying to understand heat. Let's stay with that chain for a moment, because it's genuinely one of the most remarkable threads in the history of technology. Enrico Fermi and Paul Dirac, working independently in 1926, figured out the statistical rules governing particles like electrons, particles that obey what's called the exclusion principle, meaning no two of them can occupy the same quantum state at the same time. Wolfgang Pauli had articulated that exclusion principle just a year earlier, and Fermi and Dirac built the mathematics of how enormous populations of such particles distribute themselves across available energy levels at a given temperature. And here's the thing. This is still thermodynamics. Temperature is still the key variable. Boltzmann's constant still shows up everywhere. The whole framework is about how energy gets shared among many particles in thermal equilibrium. It's the same question Boltzmann was asking in the 1870s, just with quantum rules layered on top. Now, what Fermi-Dirac statistics revealed about solids was profound. In a metal, you've got this sea of electrons, and they fill up energy levels from the bottom, like water filling a container, each electron sitting in the lowest available state because of that exclusion principle. The topmost filled level at absolute zero is called the Fermi energy, and it's surprisingly high. For copper, it corresponds to a temperature of roughly 50,000 Kelvin, which is hotter than the surface of the sun. That sounds bizarre, right? The electrons in a piece of copper wire sitting on your desk are, in a sense, occupying energy states that classical physics would associate with tens of thousands of degrees. But they can't give up that energy because there are no lower states available. Everything below is already occupied. This is why metals don't behave the way classical thermodynamics predicted. Classical theory said every electron should contribute to the specific heat, but most of them can't because they're locked in place by quantum statistics. Only the electrons near the Fermi surface, the ones at the top of that filled sea, can absorb small amounts of thermal energy and hop to slightly higher states. And that's a tiny fraction of the total, so the electronic contribution to specific heat is much smaller than classical physics expected, and it varies linearly with temperature rather than being constant. This was a triumph of quantum statistical mechanics, and it explained experimental data that had been puzzling people since the late 1800s. But the real revolution, the one that changed civilization, came from understanding what happens in materials that aren't metals. Semiconductors, materials like silicon and germanium, where the electrons fill up energy bands completely, leaving a gap, an energy gap, between the filled states and the next available empty states. At absolute zero, a pure semiconductor is an insulator. No current flows because the electrons have nowhere to go. They're all locked in filled bands with an energy gap above them that thermal fluctuations can't bridge. But as you raise the temperature, some electrons gain enough thermal energy to jump across that gap, and suddenly you have carriers that can move and conduct electricity. The conductivity of a semiconductor increases with temperature, which is the opposite of a metal, and the size of that energy gap, typically on the order of 1 electron volt for silicon, determines everything about the material's electrical behavior. Now here's where it gets practical. In 1947, at Bell Labs in Murray Hill, New Jersey, John Bardeen, Walter Brattain, and William Shockley created the first working transistor. The date was December 23rd, just a few days before Christmas, and the world barely noticed. But what they'd done was figure out how to control the flow of electrons through a semiconductor by applying a small voltage, essentially using one electrical signal to switch or amplify another. And the physics underneath that device, the reason it worked, was quantum thermodynamics. The behavior of electrons in those semiconductor junctions, the way carriers diffuse across boundaries between differently doped regions, the way temperature affects carrier concentrations. All of it is governed by Fermi-Dirac statistics and the thermodynamic concepts that Boltzmann and Gibbs and Planck had developed. Think about what that means. Sadi Carnot sits down in 1824 to analyze steam engines, trying to understand the theoretical limits of converting heat into work. A century and a quarter later, that intellectual lineage produces the transistor. The path isn't obvious. It winds through Joule's brewery experiments, through Clausius's entropy, through Boltzmann's tragic insistence on atoms, through Planck's desperate quantization of energy. But every step is connected. Each breakthrough made the next one possible. And the transistor, of course, made possible the integrated circuit, which made possible the microprocessor, which made possible the computer you might have used today, the phone that might be playing this for you right now. But let's not rush past the mid-20th century, because thermodynamics was doing other extraordinary things during this period. Let's talk about one of the most dramatic engineering applications of thermodynamic principles ever attempted: the development of the atomic bomb during the Manhattan Project. Now, nuclear weapons involve nuclear physics, obviously, but the engineering challenges of actually building one were deeply thermodynamic. Consider the problem of isotope separation. Natural uranium is overwhelmingly uranium-238, with only about 0.7% being the fissile isotope uranium-235. To build a bomb, you need to enrich that concentration dramatically, and separating two isotopes of the same element, atoms that are chemically identical, differing only in mass by about 1%, is a thermodynamic nightmare. The primary method used at Oak Ridge, Tennessee, was gaseous diffusion. You convert uranium into uranium hexafluoride gas and push it through barriers with microscopic pores. The lighter molecules, the ones containing U-235, diffuse through the barrier slightly faster than the heavier U-238 molecules. The separation factor per stage is tiny, something like 1.0043, meaning each pass through a barrier enriches the U-235 concentration by less than 0.5%, so you need thousands of stages cascaded one after another with enormous amounts of gas being pumped and recycled. The K-25 plant at Oak Ridge was, at the time of its construction, the largest building in the world, a U-shaped structure 0.5 mile long, containing thousands of diffusion stages, consuming staggering amounts of electrical power. And the whole thing is an exercise in applied thermodynamics. The diffusion rates depend on temperature. The pumping requires work against pressure gradients. The cascade design is an optimization problem balancing energy input against separation efficiency. Engineers had to manage heat dissipation across this enormous system, deal with corrosion from the fiercely reactive uranium hexafluoride gas, and maintain vacuum integrity across miles of piping. It was thermodynamics at industrial scale, pushed to extremes that would have made Carnot's head spin. And then there's the bomb itself. The implosion design used for the plutonium weapon tested at Trinity in July 1945 required understanding shock waves, detonation physics, equations of state for materials under pressures of millions of atmospheres, all thermodynamic territory. How does plutonium behave when you compress it to twice its normal density in a few microseconds? What temperatures and pressures develop? How does the chain reaction propagate? These questions sit at the intersection of thermodynamics, nuclear physics, and fluid dynamics, and answering them required some of the most sophisticated calculations ever attempted at that time, many of them done on early computing machines, and remarkably, by hand. I bring up the Manhattan Project not to dwell on destruction, but to illustrate how deeply thermodynamic thinking had penetrated every corner of engineering and physics by the mid-20th century. It wasn't just about steam engines anymore. It was about everything, every process that involves energy transformation, every system where you need to understand how heat flows, how work gets done, how entropy constrains what's possible. And speaking of entropy constraints, let's circle back to something we touched on earlier and push it further, because this is one of the deepest ideas in all of science. The second law of thermodynamics, entropy, tends to increase in isolated systems, turns out to have implications far beyond engineering. By the mid-20th century, people were beginning to understand that the second law connects to information theory, to biology, to cosmology, to the fundamental arrow of time itself. Claude Shannon, working at Bell Labs in 1948, the same Bell Labs that produced the transistor, published a paper called A Mathematical Theory of Communication that essentially invented information theory. And the mathematical quantity at the heart of his theory, the measure of information content or uncertainty in a message, turned out to have exactly the same mathematical form as Boltzmann's entropy. Shannon reportedly asked John von Neumann what to call this quantity, and von Neumann told him to call it entropy, partly because the mathematics was identical, and partly, von Neumann supposedly joked, because nobody really understands entropy, so in any debate, Shannon would have the advantage. Whether that anecdote is perfectly accurate or slightly embellished, the connection is real and deep. Information and thermodynamic entropy are not merely analogous. They are, at a fundamental level, the same thing. Landauer's principle, which we talked about earlier, makes this concrete. Erasing one bit of information necessarily dissipates at least kT times the natural log of 2 in energy as heat. Information is physical. Entropy is information. The boundaries between thermodynamics, computation, and communication theory dissolved. And this has practical consequences today that would astonish the founders of thermodynamics. Every data center in the world, every server farm humming away to keep the internet running, faces a fundamental thermodynamic challenge: getting rid of heat. The computation itself, the flipping of billions of transistors billions of times per second, generates heat. Not because of engineering imperfection, though imperfection makes it worse, but because of Landauer's principle. There is a minimum thermodynamic cost to computation. Modern processors don't come anywhere near that theoretical minimum. They dissipate far more energy per operation than kT natural log of 2. But as transistors shrink and clock speeds increase, thermodynamic limits become increasingly relevant. The engineers designing the latest chips at Intel or TSMC or Samsung are, whether they think of it this way or not, working within constraints that Carnot first glimpsed 200 years ago. And this brings us to something that connects thermodynamics to perhaps the biggest question facing civilization right now: energy. The entire story we've been following, from Newcomen's atmospheric engine to modern power plants, is a story about converting heat into useful work. And the second law has always set the ceiling on how efficiently you can do that. A modern combined cycle gas turbine power plant can reach thermal efficiencies above 60%, which is remarkable. Carnot would be impressed, but it still means that roughly 40% of the fuel's energy is rejected as waste heat. That's not bad engineering. That's physics. The second law says you cannot convert heat entirely into work when operating between finite temperature reservoirs. Every power plant on Earth, whether it burns coal, gas, uranium, or concentrates sunlight, operates under that constraint. But here's what's interesting about where we are now. The challenge of climate change has forced engineers and scientists to think about thermodynamics in new ways. Heat pumps, for instance, devices that move heat from a cold reservoir to a hot one by doing work, are essentially Carnot cycles run in reverse. They've existed since the 19th century in concept, but modern heat pumps, using carefully engineered refrigerant cycles and variable speed compressors, can achieve coefficients of performance of 3, 4, even 5, meaning for every unit of electrical energy you put in, you move 3 or 4 or 5 units of heat. That's not violating any laws. It's exploiting the thermodynamic asymmetry between work and heat transfer. And as electricity grids decarbonize, heat pumps become one of the most important technologies for reducing carbon emissions from heating buildings. Thermodynamics, the science born from trying to make steam engines more efficient, is now central to the effort to stop burning fossil fuels altogether. And then there's the question of what happens at the very largest scales, cosmological scales, where thermodynamics meets gravity and general relativity, and where some of the strangest and most beautiful ideas in all of physics emerge. Because when you start thinking about thermodynamics on the scale of the entire universe, things get wonderfully strange. And the story starts, as so many good stories do, with a puzzle that nobody quite knew how to solve. Think about this. The second law tells us that entropy increases. Systems move from ordered states to disordered states. Hot things cool down. Concentrated energy disperses. That's the arrow of time. The reason yesterday is different from tomorrow. The reason you can scramble an egg, but not unscramble one. And if you take that idea seriously, if you really follow it to its logical conclusion, then the universe itself must be winding down. It must be moving from some initial state of low entropy toward a final state of maximum entropy. A state where everything is the same temperature, where no gradients exist, where no work can be extracted from anything, where nothing interesting can ever happen again. The Victorian physicists called this heat death. Thomson, Lord Kelvin, was one of the first to articulate it clearly, back in the 1850s, and it haunted him. The idea that the universe has a kind of expiration date, not with a bang, but with a slow, quiet fading into perfect, featureless equilibrium. And for a long time, heat death seemed like a straightforward consequence of the second law. But here's the thing that makes cosmological thermodynamics so much trickier than the thermodynamics of steam engines and refrigerators. Gravity changes everything. In ordinary thermodynamics, the kind Clausius and Boltzmann worked out, a uniform distribution is the high entropy state. If you release a gas into a box, it spreads out evenly. That's maximum entropy. But when gravity is important, when you're dealing with enormous masses spread across cosmic distances, the opposite is true. A uniform gas cloud is actually a low entropy state. Gravity wants to clump things together. A smooth, featureless cloud of hydrogen will, given enough time, collapse into stars, galaxies, black holes, highly structured, highly concentrated configurations. And those clumpy, structured configurations are the high entropy states when gravity is in the picture. That's deeply counterintuitive if you've spent your whole life thinking about entropy as disorder. It seems like a galaxy full of stars should be more ordered than a smooth cloud of gas. But remember what Boltzmann taught us. Entropy isn't really about disorder in the colloquial sense. It's about the number of microstates consistent with a given macrostate. And when you include gravitational degrees of freedom, there are vastly more ways to arrange matter in clumped, concentrated configurations than in smooth, spread-out ones. The gravitational phase space is enormous, so the universe started in an extraordinarily special, low-entropy state, remarkably smooth, remarkably uniform, and it's been increasing in entropy ever since, partly by forming all the structure we see around us. Stars, galaxies, planets, you and me. All of it is entropy increasing, driven by gravity. This insight, that the early universe had astonishingly low gravitational entropy, was articulated most clearly by Roger Penrose, the British mathematician and physicist, starting in the 1970s and 1980s. Penrose pointed out that the smoothness of the early universe, as revealed by the cosmic microwave background radiation, is actually a profound mystery. The Big Bang produced a universe that was almost perfectly uniform in temperature and density. Variations of only about 1 part in 100,000. That uniformity is precisely the kind of special, low-entropy initial condition that makes the second law work going forward. If the universe had started in a high-entropy state, already clumped, already full of black holes, there would be no arrow of time, no gradient to drive all the processes we see. Penrose estimated that the probability of the universe starting in such a low entropy state compared to all possible initial states is something like 1 in 10 to the power of 10 to the power of 123. That's a number so absurdly small that it makes every other small probability in physics look enormous by comparison. Why the universe started that way remains one of the deepest unsolved problems in physics. It's a thermodynamic mystery at the very foundation of cosmology. And then there are black holes, which turn out to be the most thermodynamically interesting objects in the universe. For a long time, black holes seem to exist outside of thermodynamics entirely. A black hole, classically, is defined by just 3 numbers: its mass, its charge, and its angular momentum. That's it. No matter what you throw into a black hole, books, stars, encyclopedias, hot gas, cold gas, the black hole settles down to a state described by just those 3 quantities. John Wheeler summarized this as, "Black holes have no hair." But that creates a terrible problem for the second law. If you throw a box of hot gas into a black hole, the gas had entropy, lots of entropy, and now it's gone, hidden behind the event horizon, inaccessible to any outside observer. Has the entropy of the universe decreased? Has the second law been violated? Jacob Bekenstein, a young graduate student working with Wheeler at Princeton in the early 1970s, proposed something radical. He suggested that black holes do have entropy and that it's proportional to the area of the event horizon, not the volume, the area. This was a strange and beautiful idea. In ordinary physics, entropy scales with volume. A box twice as big can hold twice as many microstates. But Bekenstein argued that for a black hole, the entropy goes as the surface area of the horizon, measured in units of the Planck length squared. The Planck length is absurdly tiny, about 10 to the minus 35 meters, so even a modest black hole has an enormous horizon area in Planck units, and therefore an enormous entropy. Stephen Hawking was initially skeptical. He thought Bekenstein's proposal couldn't be right, because if a black hole has entropy, then by thermodynamic reasoning it must also have a temperature, and if it has a temperature, it must radiate energy. But classically, nothing escapes a black hole. That's the whole point of a black hole. So Hawking set out to disprove Bekenstein's idea by doing a careful quantum mechanical calculation of what happens near the event horizon. And what he found in 1974 stunned everyone, including himself. Black holes do radiate. They emit a faint thermal spectrum of particles, what we now call Hawking radiation, with a temperature inversely proportional to the black hole's mass. A stellar mass black hole has a temperature of about 60 billionths of a Kelvin, unimaginably cold, far colder than the cosmic microwave background and completely unmeasurable with any current technology. But the radiation is there in principle. And it means Bekenstein was right. Black holes are thermodynamic objects. They have entropy, they have temperature, and they obey the laws of thermodynamics. The formula for black hole entropy, now called the Bekenstein-Hawking entropy, is one of the most remarkable equations in physics. It connects gravity, quantum mechanics, and thermodynamics in a single expression. The entropy equals the area of the event horizon divided by 4 times the Planck length squared, multiplied by Boltzmann's constant. It's engraved, along with Boltzmann's own S equals K log W, in the pantheon of fundamental equations. And here's what's truly staggering about it. A black hole with the mass of the Sun would have an entropy of about 10 to the 77 in units of Boltzmann's constant. That's more entropy than all the ordinary matter in the observable universe combined. Black holes dominate the entropy budget of the cosmos. The supermassive black hole at the center of our galaxy, with a mass of about 4 million suns, has an entropy of roughly 10 to the 90. The entropy of all the stars, all the gas, all the radiation, all the cosmic microwave background photons. It's a rounding error compared to the entropy locked in black holes. And Hawking radiation introduces another twist. Because black holes radiate, they lose mass. Slowly, imperceptibly slowly, for any black hole we know of, but steadily. A solar mass black hole would take something like 10 to the 67 years to evaporate. That's so much longer than the current age of the universe that it's essentially forever on any human timescale. But it's not forever on the timescale of eternity. In the very, very far future, if the universe keeps expanding, all the stars will burn out, all the matter will decay or be swallowed by black holes, and then even the black holes will evaporate, one by one, each ending its life in a final burst of Hawking radiation. And after that, you're left with a thin, cooling soup of photons and particles, spreading ever farther apart in an ever-expanding space. That's the modern version of heat death. Not quite the featureless thermal equilibrium that Kelvin imagined, because the expansion of the universe means the temperature keeps dropping, asymptotically approaching absolute zero, but never quite reaching it. An eternal, cold, empty, expanding void. It's a melancholy picture, if you think about it too hard. But there's also something quietly beautiful about it. Everything that has ever happened, every star that has burned, every civilization that has risen and fallen, every thought anyone has ever had, all of it is part of the universe's long, slow journey from that extraordinarily special low entropy beginning toward the vast, featureless equilibrium of the far future. The second law of thermodynamics, the same principle that Carnot glimpsed in the workings of a steam engine in 1824, governs the entire arc of cosmic history. And you know, there's a kind of poetry in how this whole story connects. We started, hours ago now, with the simple human desire to understand heat, what it is, how it moves, why fire is hot. Ancient people felt warmth from the sun and wondered. Philosophers invented caloric, an invisible fluid, because they needed some way to talk about what was happening. Then engineers, practical, stubborn, brilliant people like Newcomen and Watt, built machines that turned heat into motion, and a young French military engineer named Sadi Carnot asked why those machines couldn't be perfect. His answer, that something is always lost, that there's always waste, that you can never convert all the heat into work, became the seed of the second law. Joule showed that heat and work are the same kind of thing, just energy in different forms. Clausius gave the loss a name, entropy, and said it always increases. Boltzmann explained why, connecting the macroscopic world of engines and temperature to the microscopic world of atoms and probability, and it cost him dearly. He spent years defending atoms against people who said they were a fiction, and he died before the world fully came around. Then Planck, trying to explain how hot objects glow, accidentally discovered that energy comes in discrete packets, and quantum mechanics was born from a thermodynamic problem. Einstein picked up the thread, and Debye, and Fermi, and Dirac, and suddenly we understood why metals conduct electricity, why semiconductors behave the way they do, why you can build a transistor. And from transistors came computers, and from computers came the information age. And Shannon showed that information itself has entropy, and Landauer showed that erasing information costs real energy, that the abstract world of bits and the physical world of heat are connected at the deepest level. Every time your phone gets warm in your hand, that's thermodynamics. Every time a data center needs cooling, that's the second law, still setting limits, still demanding its due. And now, here we are, using thermodynamics to understand the fate of the entire universe, from steam engines to black holes, from Carnot's little pamphlet published in Paris in 1824 and largely ignored for a decade, to Bekenstein and Hawking writing equations that describe the entropy of objects so massive that light itself cannot escape them. It's all one story. One long, winding, beautiful story about energy and entropy and the deep structure of nature. So as you lie there, maybe drifting in and out, maybe catching every word, or maybe just letting the sound wash over you, think about this. The warmth of your blanket, the heat of your own body, the gentle cooling of the room around you. All of it is thermodynamics. Your body is a heat engine, converting chemical energy from the food you ate into the work of breathing, thinking, keeping your heart beating, and radiating the waste heat into the air around you. You are, right now, a small part of the universe's great project of increasing entropy. And that's not a sad thing. It's the process that makes everything possible. Every sunset, every rainstorm, every living thing. Without the gradient between the hot sun and the cold emptiness of space, without the second law driving energy through the biosphere, none of it would exist. We live in the flow, in the beautiful, temporary structured eddy between the low entropy past and the high entropy future. And understanding that, really feeling it, the way Carnot and Boltzmann and Planck and all the rest came to feel it, is one of the quiet privileges of being a curious person in a universe that, for reasons we still don't fully understand, started in just the right way to make curiosity possible. So let that settle. Let the ideas drift. You don't need to hold on to any of it too tightly. The laws of thermodynamics will still be there in the morning, quietly governing everything, the way they always have, the way they always will. For now, just rest.